All right, hey Honors Chemistry. So here are video notes that we did in class, but if you were absent or needed to get a refresher, I have them for you. So this is Unit 2 information on pressure, volume, and introducing increasing and decreasing factors. So in class, you had a simulation where you had this syringe and you were able to push and pull on the syringe to change the volume. And for you, the volume was the independent variable because you were changing it to see something happen. And the something that happened was pressure, which was your dependent variable. Okay, and so here was some sample data that was collected, and you could see, or a lot of you saw, that as you increased the volume, the pressure got lower, but as you decreased the volume, the pressure got higher. And then I asked you to get the pressure at 10 milliliters. And so I'm going to tell you what I told you, that at 10 milliliters, the pressure was the highest at about 5,000 HPa. And HPa was a unit of pressure. And here is the graph that you constructed. It looked like this curve of a graph, but basically what it was saying is as V increases, P decreases. Or conversely, on the other end, as V, or as volume was decreasing, as V decreases, look at pressure going all the way up, P increases. Okay? And this shows what's known as an inverse relationship. And you're going to have to know this graph for your next unit test. And so let's put that information together. There are going to be two different types of graphs that we construct from our behavior of gas data, meaning the pressure, volume, temperature, number of particles. All other gas behavior looks like this. All other gas behavior looks like directly proportional. It goes through 0, 0. It's a line. This is as something goes up, something else will go up as well. Right? Or something goes down, something else will go down. We'll see that as a directly proportional relationship. It moves together in a straight line. But pressure versus volume is an inversely proportional relationship. And this says as P increases, the opposite or inverse to volume happens. V decreases. So for example, if I took my pressure, if I multiplied my pressure by 4, then my volume is going to be the inverse of multiplying by 4. My volume would be 1/4. So if I had a pressure of 1 atmosphere and the volume was 20 milliliters, and then I turned the pressure to 4 atmospheres, well, if I'm quadrupling my pressure, I'm doing the inverse or opposite, dividing by 4 to my volume. And so that is how those will go together. So you're going to have to know this pressure versus volume graph. No, it's the only graph that is a curve. Another graph that you're going to have to recognize is if I take pressure and I do the inverse of volume. If I plot pressure versus the inverse of volume, I get a straight line. What this graph is saying is pressure versus 1 over volume, which is the inverse of volume, is directly proportional. So it's taking this graph and changing all of the volumes to 1 over volume, or the inverse of volume, and it's a straight line. So you're going to have to recognize this graph, okay? All right, so putting this together, now we know the relationship between pressure and volume is inversely proportional. When the pressure increases, the inverse or opposite will happen to volume. Volume decreases. And when pressure decreases, the inverse or opposite will happen to volume. Volume increases. Now, the way that we could calculate this and show this is by using increasing and decreasing factors, right? An increasing factor is a factor in which I multiply, and here's my factor, this is my factor, a large number over a small number. So here's my factor. A factor is just a ratio or a fraction. We'll call that a factor. And so if I have a number and I want to show an increase, I multiply by an increasing factor. If I have a number and I want to show a decrease, I'm going to multiply by a decreasing factor. And so, for example, in the lab simulation, you had at 10 milliliters, the volume was equal to 10 milliliters, and the pressure was equal to 2,500 HPA. And then, the volume was 20 milliliters, my bad. The volume was 20 milliliters and the pressure was 2,500. And then I said, if I changed the volume to 10 milliliters, what would be my new pressure? Well, remember, what am I doing to volume here? My volume is decreasing. Right, so if I had this scenario and I had a volume at 20 milliliters, and I knew the pressure of that volume was 2,500 HPA. HPA is just a unit of pressure. And then I do something and I change the volume to 10 milliliters, I could be able to figure out the pressure. I could guess it. Now, volume is decreasing. This means that pressure must increase. And so what this means is I need an increasing factor. So I need an increasing factor on my pressure. Okay? And so the only factor affecting pressure here, the only factor affecting pressure is my volume. And so if I go and write this, here is my setup for an increasing factor. What I do is, first I write my pressure. I know my pressure needs to increase. So I write my pressure as 2,500 HPA. And I need an increasing factor. An increasing factor is a large number over a small number. Well, the only factor that is affecting my pressure is my volume, like I said. And so I'm going to multiply by a factor using my volumes. I need to put large number over small number. Between 20 and 10, large is 20, small is 10. So I'm going to put 20 milliliters over 10 milliliters. If I do this math, I will get 5,000 HPA. This is the beginning of using increasing and decreasing factors in our calculations. So, we will be using these, and for the rest of this video, I'll be doing 3 examples. If I know my pressure or volume needs to increase or decrease, I know I will be multiplying by an increasing or decreasing factor. So let's look at an example. A sample of gas that occupies a volume of 450 milliliters has a pressure of 1.3 atmospheres. Milliliters is volume, so I could put that in the table. 450 milliliters. Pressure, 1.3 atmospheres. Atmospheres is a unit of pressure. What would be the pressure of the gas at 105 milliliters? So 105 milliliters is a new volume, and it's asking for the pressure. So now I kind of have this table here, and we're going to organize this table. But now that I have this table, I could start thinking about what is supposed to happen. And the most important thing for me in chemistry is this effect, right? So what's happening to my volume? My volume is increasing. Okay? Now, since I know that my volume is increasing, sorry, that went down. Since I know that my volume is increasing, what is the relationship between pressure and volume? Well, we just talked about, and it says it up here, when pressure When pressure increases, volume decreases. When pressure decreases, volume increases. So I have an increase in volume. Oh, my bad. My volume is decreasing. Wow, whoever's doing, you're probably doing this and like, what, Mr. T? Sorry. So my volume is decreasing. It's going from 450 to 105. And so if I have a volume being decreased, my pressure needs to increase. So increase, which means I need an increasing factor. Okay? And so now what I do is the only factor affecting pressure here is my volume. Affecting pressure is volume. So I'm going to need to make an increasing factor from my volume. And so the way that I start setting this up is I start with 1.3 atmospheres because I need to show an increase in my pressure. If volume decreases, my pressure is going to increase. So I need to show an increase on my pressure. So I need to multiply by an increasing factor. Up here, an increasing factor is a large number over a small number. So my large number is 450 and my small number is 105. So I do 450 milliliters over 105 milliliters. And this is just like in dimensional analysis when you did this type of calculation. You're going to do 1.3 times 450, and then you're going to divide by 105. You multiply by 450, and then you divide by 105. So I'm going to do 1.3 times 450 divided by 105, and it looks like my pressure is 5.57 atmospheres. Now, if I wanted to have the correct number of sig figs, this has 2 sig figs. 450, that 0 is not significant because there's no decimal point. 2 sig figs. And then this has 3 sig figs. So my answer needs to have the least number of sig figs if I'm doing a multiplication and division. SF. So I need to convert 5.57 to 2 sig figs. So this is going to be about 5.6 atmospheres. Okay. So this is just the beginning of using increasing and decreasing factors. Let's do another problem. All right. So example number 2, it says a sample of, and I'm not going to make a typo or a right-o this time, a sample of gas that occupies a volume of 50 milliliters, so that's my initial volume, has a pressure of 755 millimeters of mercury. Cool. That's another pressure. What would be the pressure of the gas at 92 milliliters? Okay, so I'm not going to make a mistake this time in writing it. I'm going from 50 to 92 milliliters, so I'm increasing in volume. And now remember, pressure and volume are inversely proportional. So if I increase in volume, I need to decrease in pressure. So I need a decreasing factor. All right, and so now I'm going to set this up. A decreasing factor is one that has a small number over a large number. And again, the only factor affecting my pressure here is my volume. There's no temperature, there's no number of particles. The only factor affecting my pressure is my volume. So I need a decreasing factor from my volumes. So I'm going to start by writing 755 millimeters of mercury. And if I want a decreasing factor, I need to put a small number over a large number. Well, between 50 and 92, my small number is 50 milliliters over 92. So 755 times 50 divided by 92. And I get 410.326. 410.326. And it's going to be millimeters of mercury. Okay. And again, why did I do it this way? My volume increased. Pressure and volume are inversely proportional. So whatever I do to my volume, I do the inverse or opposite to my pressure. Now I need to decrease my pressure. I need a decreasing factor. The only factor that I could make and use is from volume. And so I'm going to put 50 over 92, and I get this. Now for sig figs, this is 3 sig figs. This is 1 sig fig. That 0 is not significant without a decimal point, and this is 2 sig figs. I need the least number of sig figs in my answer. If I want to round 410.326 to 1 sig fig, it's going to be about 400 millimeters of mercury with 1 sig fig. Okay? All right, I'm going to leave you to try and do example number 3 on your own. If you are absent, show this to me. Show this to Mr. T. If you were absent or wanted to get more practice, show this to me, and I could verify and check to make sure that you did example number 3 correctly so you could be on the right path.